And here I've started recording. You guys, if I ever don't start well, I don't know if you can see if it's recording or not. I've had trouble remembering to record meetings. So, you know, if I don't say something like, okay, I'm going to start recording, maybe somebody like beyond that and be like, hey, you need to start recording. Because it's been a problem. Okay, we're still at 22. Okay, it is recording though, you guys, and it is time to start. So I'm just gonna go ahead. So let's talk about what we did last time. So last time, we did the average rate of change, right? And basically what that related to was picking 2 points on a function and then calculating the slope between them. So it was like a slope. Even though our functions weren't straight lines, we linearized them between 2 points and then we calculated their slope. So let me review for you how off that can be when it comes to talking about how a function is changing. So, and we even just looked at a quadratic function. So I just made a parabola, which is the, let's call it the second most simple function that you could make, right? And depending on where the 2 points are that you pick, it was still way off. So I had a point like here, and remember its point on the function was like here. We had a B. Ooh, I picked a B badly. I need some more graph. So B would be here. And remember what the average rate of change was doing was just drawing a straight line between those points and calculating that slope. So this space here is all the error that I get when I calculate that average rate of change. I can say the slope of this line, but it's not super accurate. There might be areas where it's more accurate than others. You know, if you kind of see the curve going in a semi-parallel direction to our slope, but there's so much wrong, right? But I think I can get it a little better, and I'm going to show you how we can reduce that error. So again, this picture is just a recall of last time. You should already have that written if you don't want to write it again, but if you do, it's a good representation of our average rate of change. Now I'm going to draw this picture a little bit larger. I'm going to try to take up as much board as I can because I'm going to change some things as we go. You guys, and I am going to stick with the simple quadratic. So you've got your function and you pick your A and B. So notice the average rate of change is always just going to be a slope between 2 points. The one thing you have control over is those 2 points. So maybe it would help if they were closer together or further apart. Maybe let's play with A and B in their position on my function and see if I can get a little bit closer to an actual rate of change. Okay, so we started with A and B being pretty far apart. So let's see, on this graph, here's the output at A. We put B over on this other side. And then we calculated the slope between them. So I'm going to draw that. Oh, that's a good one. Okay. So we had this and we had a lot of error, but I want to cut down that error. What if I change where B is? What if I made B come closer to A? Do you think that would help or hurt? Let's call it B1. So I just got a little bit closer. You guys, if X is here instead, then the point on the function is down here. So here's the point now. Here's the second point. And notice I haven't changed A at all. But if I were to calculate a slope between these 2 points, Did I effectively cut down the error there? The space between the function and that straight line? It got a little closer, right? So that's a good sign. You guys, so I say, ooh, if I just move B a little closer, when I calculate the average rate of change, it's gonna be a little more accurate. It's gonna be a little more like what the function is actually doing here. Let's make it closer. Like really close. Let's call this B2. And now my B is here. Notice I haven't moved A, I'm just moving one of them. But here's a new B point. Where is its output? It's right here. So you guys, look at the little space that I'm taking between A and B. This still is not a straight line. I still have to draw a straight line through these points, starting at A and going to B. So even though it's hard to see, even on a large graph, this would be hard to see at this point. There's a little bit of error. There's always going to be a little bit, but look how much better it is. Now there is a drawback. You guys, this first large one that I did, I was averaging the rate of change, and no, it wasn't a great value. It gave us a lot of error, but it covered a larger portion of the graph. I could say this is kind of like how the function is changing between these 2 points. So this is a big section of your graph. Now, as you go down, we're getting more accurate, but the portion of our graph that we're covering is just less. And you guys, honestly, quality over quantity here. If you can be this accurate, I would rather know what was happening in a tiny portion of the graph than what was happening kind of on a big portion of the graph, right? And you guys, I could always just do this in multiple places. And then I would have more of an understanding of how this function is changing. So you guys, the closer A and B are together, the better. Why stop here, guys? Why don't I just keep getting closer and closer? You guys, what if I had a B right here? Could you imagine the distance between these 2 tiny points is almost a straight line anyway? And you don't have to necessarily draw that one, that's a tough one. But you guys, the closer B gets to A, the more accurate your linearization is. So optimally, what if we could somehow get B infinitely close to A? And you guys, that is what our goal is. We're going to try to accomplish finding the average rate of change for something as B gets infinitely close to A. Now I do say infinitely close, and I don't, notice I've never said B equals A. That would be an interesting place. That would just be 1 point. And that honestly is where I want to go, but that's not where I can go. So let me show you why not. Found it. So just from what the picture shows me, it looks like I want B and A to be really close together, because the closer they are, the more accurate my change calculation is. But B and A can't be so close that they're the same point. Let me show you why. Remember what we're calculating. And I am going to put it in the function notation form. I know it's always just changing y over changing x. But remember, I have a formula for it. This f of b minus f of a over b minus a. What happens to this formula if a and b were the same value?
Undefined?
Right, it would be undefined. You guys, if A and B are the same and I'm subtracting them from each other, I would get a 0 on the bottom. So it's like, oh man, well that kind of sucks, because that's kind of what I want to define. I want to define this super accurate straight line that mimics the graph at the smallest point imaginable, which would just be 1 instantaneous point. But I can't, because it doesn't exist. So instead, this is why we've talked about limits up to here. Remember, with limits, I don't care if it actually exists, right? I just care what it's approaching. So it's like I have a way now to get around the fact that this doesn't exist I can use limits to help me. Now, I am going to do that, but first, I need to work with this formula a bit before I can start taking the limit of it. So one thing that we do in this formula, because we've got these 2 points A and B, and you guys, what you're going to find is that the value we're looking for is actually going to be a point where B and A are the same. Even though it seems impossible, we're going to get there with limits. So I only want 1 point, either A or B in here, and I'm going to choose that I want A. So here's what I'm going to do. We're going to introduce a new variable, H. I promise H will make this look better, even though it seems like I'm adding a third variable for no apparent reason. I'm going to let H be the difference between A and B. So B minus A, what I have here on the bottom right now, I'm going to change it and I'm just going to say, well, let's just call that H. Now let's talk about what H represents. Think about that graph that I made and B was getting closer and closer to A. So if B minus A is really just H, H is actually representing the space between A and B. So when you think about H, I want you to think about the difference between A and B. And my goal is to get H to be really, really, really small. If H equals B minus A, then I can put an H here. But my goal right now is to get rid of the B in this because I'm going to keep A. Obviously, I'm going to keep H because I'm introducing that to the problem. But B is what I want to get rid of in this formula. So I've got it covered here. I can just put an H there instead. But I got a B up here I got to deal with. So notice that this B here is just a B by itself. It's not B minus A. So I can't just put H there. I need to figure out, I'm going to use this substitution form I have here. And I'm going to get B by itself. And I'm going to find a way to replace B with a combination of A and H. So basically, take this here that I just said was true, solve for B. Looks like I just have to add A to both sides and I'll get there. So as long as this is true, which it is because that was our decision, right? We arbitrarily said that this is true. Then this would be true too. So this B that's right here, I'm going to replace it with A plus H. So it looks a little more complicated than just a B, but remember my goal here was to get B's out of the equation and put H in. So let's change this. So this equals this, written in a different way, written in terms of A and H instead of A and B. And it's going to look like this. Instead of F of B, we'll have F of A plus H. That F of A stays the same. And on the bottom, remember, instead of B minus A, we're just going to have an H. So you guys, this is very important to us. Very super, the most important thing today is for you to know this particular form. Notice it doesn't look anything like average rate of change. I mean, maybe a little bit, but when you look at this, it doesn't just scream, hey, this is just a slope calculation, right? I mean, it looks a lot different than this does, but this is just an average rate of change. So now we know how to find average rate of change with the H instead of the A, or instead of the B. But still, if these and this are the same, then this is still going to give me as much error as this did, just with different letters, right? So what am I missing here? What am I missing? It's that, that availability to get closer and closer, to get those points A and B closer and closer to each other, right? It's the approach that I'm missing. It's the A and B are getting infinitely close together part that I'm missing. So let's add that. So this is average rate of change, again, just in a different form. I'm going to change the name and I'm going to put a limit in there and I'm going to talk about what it means. So this is an average rate of change. What I'm going to find when I take the limit of this at a certain point is what we call the instantaneous rate of change. So when I say the word instantaneous, so you've got a graph, right? And we had an A and a B. And I kept getting this point closer and closer to the first point, right? So it gets closer, it gets closer, it gets closer. We had this line, then we had this line, then we had this line, then we had this line, and we were really close. And our rate of change was getting really, really accurate, right? But remember what my goal is. I want to get it the most accurate it could possibly be. So I have to get closer. So I did this and I was like, oh, that looks like it, guys. I mean, it looks basically right, but it's basically right isn't right. So I could get closer. You guys, what I find is if I can actually find a way to put a value on the point where A and B are the same, what this is going to give me is a straight line, first of all, because it always gives us the slope of a straight line. This is a slope calculation. But look at this line, and it's a little hard to see, and let me see if I can make it bigger. So you've got a function. Let me pick a different point. Let's say this is your point A, and you've brought B into that, and you've done the calculation, and you get this straight line. So either here or here, there are certain characteristics about this line that I want to talk about. First of all, notice it only touches one point on the function. You guys, this is why this is instantaneous. The slope of this line is going to tell you how the function is changing at one instantaneous point. If you move over a little bit, this isn't telling you anything. You guys, it only tells you at this one point. So this is a straight line, has a slope, but it only touches at, in this case, we're calling that A, right? So we got rid of B, we turned it into A, and now we're looking at an instantaneous rate of change at the point A. So over here, if this was your point A, notice, straight line, I can calculate the slope of this line, but it only touches the function at that one instantaneous point. If I moved up a little bit and I drew a similar line touching the function just like that, it would have a different slope, right? It only applies to one point at a time. So this is an instantaneous rate of change. And you guys, let's give this line a name. If you have a straight line that touches a function at one particular point, just like these two, we call this a tangent line. So just remember the word tangent line. When you calculate this instantaneous rate of change, the slope that you're calculating is the slope of a line that we call the tangent line. And I will word that in a certain way when we do a question. But right now you can just know that this is called a tangent line and we are on our way to calculating it. Okay, so instantaneous because it's only valid at one single point, which you guys, seems like a drawback, right? Well, this only gives me one particular point. And could you imagine how tedious it would be to calculate an instantaneous rate of change at a bunch of different points on the function? It would be absolutely tedious. So that's definitely a drawback, but what's the great part is that at that point, this is exactly how the function is changing. It's not kind of there. It's not, oh, with a certain margin of error. It is exactly how the function is changing. So we want to be able to find that. Here's how we do it. So instead of the A rock, we're going to have the I rock. Instantaneous rate of change. How to turn average into instantaneous is really easy. I add the limit statement. You guys, I'm going to take the limit of this. So you guys, we can go ahead and write all of that again. The limit of f of a plus h minus f of a all over h. Here's the kicker. Here's what I really need to get right. Sorry, I'm going to move this h up a little bit. I need to think about my approach. What do I want to approach? First of all, in this problem, remember we choose a value for a, or I give you a value at the beginning of the problem for a. A is not what's changing here. A is going to be a fixed value. The only thing that could change in this function or this expression is the h. What was h again? H is the distance between those 2 points A and B. What do I want to happen to those 2 points? I want them to get closer together until they are 1. I can't call them 1 because remember that put a 0 on the bottom, it was a problem. So as A and B get infinitely close together, h, the distance between them, gets really small. It looks like I want h to approach something very small. Even more than that, I want it to approach 0 as the distance between these 2 points comes to nothing is what I want to find. So my limit is going to be as h approaches 0. So guys, this is very important that you know this. So I'm going to stand and make sure you guys get this written down, and then we're going to use it a little bit. So I know it seems like a lot of concept and a lot of drawing to get us to this point, but I promise we'll actually use it now. And at least now when we use it, you know what we're looking for. So everybody has that down, limit as h approaches 0 of f of a plus h minus f of a over h. It's in its formula, it looks more difficult to use than it is. I say that depending on the function you're working with.